All right, so what I want to do now is I want to use the ratio and the root test to look at a few different series and to determine whether the series converge absolutely, whether they converge conditionally, or whether they diverge. Okay, and so let's use the different tests that we have, and we'll go from there. So let's look at our first example. Let's look at the sum of -1 to the n over, -1 to the n times n all over 5 to the n. Okay, and let's look at the sum as n goes from, say, 1 to infinity. Doesn't matter if it's 1 to infinity or 0 to infinity. What we can do here is we can actually use the ratio or the root test. If you find one easier than the other, that's totally fine. I should add here, I want to do the root test just to emphasize one thing here. The ratio test is just as easy. But the root test says, look at the limit as n goes to infinity of the nth root of the absolute value, -1 to the n, times n, over 5 to the n. And we're going to take, I forgot the absolute values, but we need to add that in there. I'm going to take the absolute values there. And when I take the absolute values, of course, the power of -1 in the numerator goes away. So this is now the nth root of n over 5 to the n. And so this is the limit as n goes to infinity of n to the 1 over n all over 5 to the n, but we take the nth root, so it's just 5. We proved in class that if you take n to the 1 over n, this is technically an indeterminate. We have to call this limit L or something, and then apply L'Hopital's rule. So we take a log, apply L'Hopital's rule, blah, blah, blah. But it turned out that this limit is 1. So just remember that we proved in class that the limit of n to the 1 over n as n goes to infinity, that's 1. And this is a fact that's going to be very useful for us, just like it was here. Okay, so when we do the root test, that limit is 1. You could have also done the ratio test, and I'll leave it to you to do the ratio test, but it turns out that the limit you're going to get is also 1/5. And so your conclusion will be the same. If this limit is 1/5, that's less than 1, and therefore the series converges absolutely. Okay, so we got absolute convergence. So not much more to say there. Let's look at the sum of 2n factorial over n factorial squared. We're going to look at the sum from 0 to infinity. Okay, and so what I want to do is let's apply the ratio test. The ratio test is going to be nicer here because when you have factorials, factorials are not powers of anything. There's something called Stirling approximation, which shows you how to write the factorial as a power. It turns out that the factorial is basically something like n over e all to the n power. So just very roughly, n factorial is approximately n over e to the n power. But we don't need to do that. That's a little bit too fancy for us, and I didn't actually establish the exact asymptotics there. That formula is close to being right, but it's actually not quite right. It turns out that it's just easier when you have factorials to use the ratio test. And so that's what we're going to do. And so let's look at the limit of as n goes to infinity. Now notice that I don't have any powers of -1, so I actually don't even need the absolute values. But we're going to end up with 2 times n plus 1 factorial over n plus 1 factorial squared divided by 2n factorial over n factorial squared. And dividing by a fraction is the same as multiplying by the reciprocal. Once we know that, and once we write out a few examples of evaluating this limit, it's going to become pretty natural just to do that. But this is 2n plus 2 factorial over n plus 1 factorial squared times n factorial squared all over 2n factorial. And let's simplify here. This is going to end up being the limit as n goes to infinity. Let's see what simplifies. N factorial over n plus 1 factorial is going to end up being n plus 1. And because we're squaring those, that means we're going to have an n plus 1 squared in the denominator. 2n plus 2 factorial over 2n factorial is going to be 2n plus 2 times 2n plus 1. And it turns out that this limit's going to be about 4. That's bigger than 1, and therefore the series diverges. Okay, so that's how we can apply the ratio test to talk about this series as well. Okay, and like I said, I'll save more examples for class. Okay, so we'll do those together, but this should give you an idea of basically what we've done in this section is quite a lot. So in section 11.6, we talked about absolute convergence, conditional convergence, and then divergence is still divergence. We didn't mess with that. We also talked about 2 new tests, namely the ratio test and the root test. And when we calculate those limits, determining whether that limit is bigger than 1, less than 1, or equal to 1 tells us something about that original series. Okay, so that's 11.6 in a nutshell.